In this lesson, we're going to discuss the bending of a structure. And so, bending an object, as we're going to soon learn, causes both a shear stress and a normal stress within this structure. Now, before we can jump in and calculate these shear and normal stresses, we need to know a little bit about this material, the cross-section of this structure, and we need to have a way of being able to deduce what a shear force and a bending moment is given a various loading on this structure. And so, before we get into the stresses, we're going to talk a little bit about kind of a review of some statics concepts, such as moments of area or moments of inertia, centroids, and the ideas of looking at a beam that's being transversely loaded, how can we extract the shear force and the bending moment and be able to calculate what the maximum values of those along the beam are. And so we're going to start by considering an arbitrary cross-section. And so I've drawn one here. This is just some strange shape. The purpose of this shape is that there's no symmetry here. It's just a random oriented structure. And we're looking at a cross-section on the x and y axis. And we're going to consider a small differential area here in blue. And what we want to first calculate is what's known as the first moment of area. And that's the sum of the area here and the distance from that area to each axis. And so what that means is we can write our first moment of area and so we'll have this first moment of area about the x, qx is going to be equal to the integral of that area and so it's going to be the integral of the distance y and the integral of that area is going to give us the first moment of area. The same thing is true in the other direction. We can write that as the integral of x over our little differential area element there. The reason why we want to be able to calculate this first moment of area is going to come up in two different places. The first place it's going to come up we're going to discuss right now, which is it's going to allow us to directly calculate the centroid of a cross-section. The second place where this capital Q, this first moment of area, shows up is in calculating the transverse shear stress in a bent beam. And we're going to come back to that and see that at a later time. But for right now, what we want to consider is the centroid. And this should be a familiar topic to you. But if not, what the centroid is describing is the average x or y position of an area. And so in the case of, say, the centroid in the x direction, it's going to be equal to the first moment of area sub y divided by the total area. And so what this looks like from our definition up here is an integral of x over the area over simply the total area. So in this case, this would be the average x position of the area. We can write the same type of formula out for the average y position. In this case, it would be qx over a, or the integral of y dA over the integral of dA. We've written it in this continuous form because the way we've drawn here, we have some arbitrary cross-section. Lots of times what you'll actually be dealing with is a cross-section that you can break up into a simpler form. So let me give you an example. If we had something that looks like, say, this, what we could do to calculate this cross-section is instead of dealing with an integral, we could deal with splitting this up into some known shapes that it's easy to calculate the area of and the centroid of. And so what we see here is we can split this up into a triangle, and a square. And in this case here, this square has a centroid that's going to just be half the height of it, and we can easily calculate the centroids of each of these two triangles, and we should usually be able to get the areas of these just from simple geometry. And so what that allows us to do is, instead of writing it in the form of an area, we can write it as a summation. And so I'll write this below here. We can treat the average x position of the area as the sum over all the elements of the centroid of each element. So that would be, say, the position along the x-axis of this area, times the area of each element. So it would be x bar sub I and a bar sub I over the sum of the total areas. I'm writing the bar here to indicate that I'm talking about kind of each one of these. So we'd have 1, 2, and say 3. And so our centroid would be adding up all of the centroids of each individual section here times its area divided by the total area. So that'll allow us to calculate the centroid of a given cross-section. Luckily, there's a few ways that this process can be simplified. And the simplification of a first moment of area comes about when there is symmetry of a cross-section. So symmetry of a cross-section. So now let's look at a different cross-section here. And in this case, we'll draw it to look like this. And so if this is our cross-section now, what we can see is that there's a symmetric axis right down the center of this thing. So this is symmetric about this red line here. And what that means is we know if there's a symmetry, then the centroid has to lie on that axis of symmetry. So the centroid of this object has to be along here. So we inherently know the x position of the centroid, and now we're just left calculating the y position. So if the centroid has to lie on an axis of symmetry, you can see that this gets even easier if instead of one axis of symmetry, we have two. So in this case, this object is symmetric about its center down the y-axis, and it's symmetric about its center along the x-axis. And so we know, just by looking at this symmetric structure, that the centroid has to lie where that orange dot is. So one thing we would do, which I didn't draw here, is if we know where the centroid of the structure is, the best way to start solving a problem is to kind of move our axes to lie along that centroid. So once we look at this shape and say, all right, well, the centroid has to be here, we can go back in and say, well, I'm going to call my axes starting from there, so our origin lies at the centroid of the cross-section. So this is our first moment of area. This is how we use the first moment of area to calculate the centroid. And most commonly you're going to see it done in this form here, where we can break up a complex structure into simple ones. And oftentimes, especially with engineering structures, there's usually either one or two axes of symmetry which allow us to simplify the problem. So this is our first moment of area. It's useful for calculating the centroid, and it's going to be useful for calculating the transverse shear stress. Another really important quantity that we're going to describe is our second moment of area, or sometimes called the second moment of inertia. So our second moment of area is defined in a very similar way. It's denoted with a capital I, and just like before, we would have capital I sub x. So the second moment of area about the x-axis is going to be equal to the integral of, in this case, it's y squared dA. And so we can write similar form for I sub y, which would be the integral over the area of x squared dA. So in solving the problems involving torsion, we used an equivalent of this property here, the second moment of area, but we used what was called the polar second moment of area. And that refers to, in this case, instead of the distance of this area to the x-axis, or the distance to the y-axis, the polar second moment of area goes from the center of this area to the origin radially, and it's using the polar coordinate system and is defined by rho. And so you'll recall that in polar coordinates, our second moment of area is the integral of the area of rho squared dA. And so what you can see here is there's a nice triangle built right in to this. So we have on the base here a distance x, a distance y, and we know from Pythagorean theorem that rho squared is going to equal x squared plus y squared. So if we want to get the second moment of area, instead of being in polar coordinates, if we want to bring it into Cartesian coordinates, we can replace rho squared with our geometric relation x squared plus y squared. And so what that looks like is the integral of the area x squared plus y squared dA. We can split this thing up, and so it would be the integral of the area of x squared dA plus the integral of the area of y squared dA. And hopefully you can immediately see that the second term is I sub x. That's the second moment of area in Cartesian coordinates about the x-axis. And this first term corresponds to the second moment of inertia about the y-axis. So another way to write J, if we want to get it in terms of Cartesian coordinates, is simply Ix plus Iy. So far we've discussed how to calculate the first moment of area of a cross-section, the object's centroid, and the second moment of area. And we've done the second moment of area from the x and y axes. And oftentimes what we'll actually want to be able to do is to calculate that second moment of area of some arbitrary point, say dA here, relative to the object's cross-section. It's the centroid of its cross-section. And so what we can do is apply the parallel axis theorem, which says we can calculate the second moment of area of any point that's parallel to this centroid. And so what we end up needing to do is kind of redefine our new axes that run through this centroid. And so what that looks like here is we'll create a new x-axis that runs through the centroid, call it x prime. We'll do the same thing in the y direction. We'll call that y prime. Now what we can simply do is to calculate the distance of this area from these axes, which are defined at the object's centroid. And so what that looks like is now we have a new distance. So for the distance of the area to the x-axis, we denote it by y. And so what we can do now instead is denote the distance of that area to the x prime axis as y prime. We can do the same thing here. The distance of this area to the new y prime axis we'll call x prime. So now what we need to know is what's the distance of our centroid to each of these axes. So we have the area to the centroid as y prime and x prime. And now we're going to take the centroid to each axis. So we'll go down here. And we'll call this d sub y. And we'll do the same thing over here. We'll go from the centroidal axis over to the y-axis. And since we're moving in the x direction, we'll call that d sub x. And we know from our initial formula of the second moment of area that if we take, say, I sub x, that's going to be equal to integral of the area of y squared dA. And so that was in reference to this y here. We can just redefine this. Instead of it being in reference to y, we know that y prime plus dy, so the distance from here to here, is equal to the same thing. And so what we can do is we can go back and recalculate I sub x as the integral over the area of y prime plus d sub y over the area element dA. And so if we do that, we can simply distribute through this area element and have this look like the integral of the area of y prime squared dA plus dy. We'll pull this outside the integral, and there'll be two of these times the integral of y prime dA plus simply the integral of the area dA with a dy squared out front of it. So all I've done here is kind of expand out this square terms in the bracket, so you end up with y prime squared dA, 2 dy times y prime dA, plus dy squared dA. And so we can immediately note a couple of things. The first thing is that the integral of the area of y prime squared dA, this is just simply I bar sub x prime, which means this is the same definition as this one, but it's just talking about it relative from our new point here, our new axes. This term here, this integral, we know to be equal to qx, right? The first moment of area. And we know that qx is equal to the location of the centroid times the area. In this case, we just said that we redefined our coordinates so that the centroid is located at the origin, which means that our first moment of area has to be equal to 0. And so this whole term goes away. And this one's a pretty straightforward one. We can just simply integrate this, and what we're left with is the area times d sub y squared. And this leads us to the parallel axis theorem, which says that the second moment of area is equal to second moment of area of this point plus a term that accounts for the distance of the area that you're looking at away from that centroidal axis. And this same definition, you can check yourself and go through this on your own. You can do the same one for I sub y. And so this is what's known as the parallel axis theorem. It'll become very useful when we have to calculate the second moment of area for, say, composite structures. What we're gonna do is essentially break up these structures into different elements, calculate the second moment of area about those elements, and then we have to account for the distance of those elements away from the total area's cross-section. So far this seems to be a little bit of a abstract definition of I. So what I want to do now is just to show you how to put this into a usable form. And so what we'll do is we'll consider a very common shape, a rectangle. And we know that because there are two axes of symmetry on this thing, the centroid has to be right at the center of the object. So what we can do is we can redefine our axes such that we have our axes run through the origin of this object. And so this will be x, and this will be y. And what we'll do is we'll denote the height of this thing by h, and we'll denote the width of this rectangle by b. And so what we're interested in getting now is let's say for starters we want to know the second moment of area about the x-axis here. And so we know we can write that down. The second moment of area about the x-axis is just an integral of the area times y squared dA. The integral of y squared dA, we know what we're integrating over here. We're going to integrate over this cross-sectional area, which means we're going to integrate from b minus 2, b over 2, to positive b over 2. So it'll look like the integral along the width component, so I'll take negative b over 2 to b over 2. That's corresponding to this. That's one integral. Our second integral is going to be the same thing, but in terms of the height, so it'll be negative h over 2 to h over 2. That corresponds to this distance. Since this is all because of where we defined our origin. And then we're going to integrate this over y squared dy dx. And so this is a fairly straightforward integral to evaluate. So we can do the first one. I'll move this down here. And such that we'll still have our integral from negative b over 2 to b over 2. And integrating this first one is going to give us 1/3. And it's going to give us, I'll just write it out explicitly, it'll be h cubed over 8 plus h cubed over 8. And so that's simply h cubed over 4 times 1/3. So it'll be the integral from negative b over 2, b over 2 of h cubed over 12. And we're going to integrate this one over dx. There's no x term in the integral, so this one simply becomes bh cubed over 12. And so in this configuration here, the way we define it, the second element of area about the x-axis is bh cubed over 12. You should be able to now do a similar analysis, and you should be able to show on your own that the second element of area about the y-axis here is going to equal b cubed h over 12. So check yourself to make sure you can see how to actually implement this formula for simple geometric shapes. You should be able to do this for triangles and circles. And what we'll find out is that combining these types of shapes, rectangles, triangles, circular cross-sections, will typically allow us to get the cross-sectional area of most engineering structures.